Welcome to an exploration of the fundamental forces and phenomena that shape our universe, from the infinitesimally small to the unimaginably vast. We delve into how deterministic large-scale behaviors, like gravity and light propagation, intertwine with subtle, emergent quantum effects. Together, these principles govern everything from nanometer-scale stiction to the catastrophic implosions of black holes. Our journey will reveal the intricate dance between the classical and quantum realms. We will examine how these seemingly disparate domains converge to define the very fabric of reality. Understanding this interplay is crucial for students, engineers, physicists, and researchers alike. The Casimir effect is a remarkable manifestation of quantum mechanics. It describes a force that arises between two uncharged, conductive surfaces placed extremely close together, typically a few nanometers apart. This force originates from the difference in allowed electromagnetic modes between the plates compared to the outside vacuum. The resulting net force can be either attractive or repulsive, depending on the specific geometry and materials involved. At submicron scales, the Casimir force can become surprisingly strong, sometimes equaling atmospheric pressure. This phenomenon is a critical consideration in nanotechnology. Engineers must account for the Casimir effect in the design of microelectromechanical and nanoelectromechanical systems, known as MEMS and NEMS devices. It is a primary cause of stiction, where components adhere unintentionally, hindering device functionality and reliability. Mitigating this quantum force is essential for advancing miniaturized technologies. Light or electromagnetic radiation plays a pivotal role in our understanding of the universe. In a vacuum, light travels at an exact and universal speed limit, 299,792 mole 458 meters per second, denoted as c. This constant underpins the theory of relativity and represents the maximum speed at which information and massless particles can propagate. When light passes through a material medium, its speed decreases. This reduction is quantified by the material's refractive index. For instance, light slows by approximately 1.5 times in glass. While its speed changes, the fundamental constant c remains the ultimate limit for any local interaction. The electromagnetic spectrum encompasses the entire range of light, ordered by frequency and wavelength. It spans from low-energy radio waves, through microwaves, infrared visible light, ultraviolet, X-rays, and finally to high-energy gamma rays. Each segment of this spectrum carries unique information about the universe, though human eyes can only perceive a tiny fraction of it. Gravity at large scales is the dominant force shaping cosmic structures. It is not merely a force of attraction, but a manifestation of mass and energy curving space-time itself. Objects from planets to galaxies follow these curves, resulting in orbits and tides. Gravity also affects light, causing it to redshift as it escapes a strong gravitational field. In extreme cases, gravity can become so intense that the escape velocity exceeds the speed of light. This leads to the formation of black holes, which are solutions of Einstein's general relativity. A black hole is defined by its event horizon, a boundary beyond which nothing, not even light, can escape. These enigmatic objects form from the gravitational collapse of massive stars or grow to supermassive scales at the centers of galaxies. Their presence is inferred through their gravitational and electromagnetic signatures on surrounding matter. At the heart of quantum mechanics lies the concept of quantum indeterminacy. This principle states that for certain pairs of properties, such as a particle's position and momentum, it is impossible to know both with arbitrary precision simultaneously. Instead, quantum states provide probability distributions for measurement outcomes. When a measurement is performed, the possibilities collapse into a definite result, but the outcome itself is inherently probabilistic. This fundamental indeterminacy is not a limitation of our measuring instruments, but an intrinsic property of nature at the quantum level. It underpins many peculiar quantum phenomena. Quantum indeterminacy is crucial for understanding effects like quantum tunneling, where particles can pass through energy barriers they classically shouldn't be able to overcome. It also provides the theoretical foundation for the Casimir effect, demonstrating its quantum origin. Implosion describes an inward collapse, typically driven by an external pressure exceeding the internal structural support. This phenomenon can occur across vast scales, from microscopic bubbles to celestial bodies. The mechanics involve a differential pressure, leading to a rapid, destructive inward movement. In astrophysics, the core implosion of a massive star can trigger a supernova explosion, leaving behind a dense neutron star or a black hole. This gravitational collapse is one of the most energetic events in the universe. On Earth, implosions can occur in engineering contexts. Vacuum vessels, deep-sea submersibles, or even buildings can suffer catastrophic implosion if external pressure differentials exceed their material strength. Understanding and mitigating implosion risks are critical in fields ranging from aerospace engineering to naval architecture. The universe presents a fascinating dichotomy, where scale dictates the dominant physics. Quantum forces, like the Casimir effect, are paramount at nanometer to micrometer scales, dictating the behavior of advanced materials and devices. Conversely, gravity reigns supreme at kilometer to astronomical scales, governing planetary orbits and galactic dynamics. Engineers face significant challenges in bridging these scales. Nano-device reliability, for instance, hinges on effectively mitigating Casimir stiction. Similarly, deep-sea and aerospace designs must meticulously account for implosion risks, ensuring structural integrity against immense pressure differentials. Our understanding of many quantum effects is often indirect, inferred from experimental results rather than direct observation. Black holes, for example, are not seen directly, but are inferred from their profound gravitational and electromagnetic signatures. These observational limits underscore the ongoing quest for deeper scientific insight. Would you like a deeper dive into how the Casimir force is measured, the mathematics of light propagation and relativity, or black hole observational evidence and images?